So, hello everyone. My name is Sara Todorovikj, and today I'm going to be presenting about our paper on the cognitive adequacy of non-monotonic logics. We'll start with a short introduction, then I will explain a little bit about the kind of data that we used here, a little bit of preliminaries in order to understand what we were using, namely inference patterns, and then we will talk about how to explain human inferences with our approach. So that is our contribution, which will be discussed in the end. So let's start. So we have this reasoning task. So imagine you're presented with this. You are told that if a balloon is pricked with a needle, then it will pop. Then you're also told that a balloon is pricked with a needle, and then you're asked, what do you infer? I assume that quite intuitive answer to this for everyone would be that the balloon popped. But then imagine that you're also presented with additional information that the balloon is in fact without air, so it is empty. And you're again asked, what do you infer? Would you still infer in this case that the balloon will pop? Most likely not. So we're going to be dealing with such tasks here. However, in our scenario, we will not be asking what do you infer, but we're talking about tasks where people are asked how likely is it that something will happen. In this case, they would be asked how likely is it that the balloon would pop. To that, they're supposed to answer with an endorsement, which is in the form of a probability value in the range between 0 and 100. The contents of tasks that we will consider here, they will all have some sort of disablers and alternatives that are associated with them. So for example, with our little balloon example, that will be a running one in this presentation, we could have the additional information that the balloon is without air, and that is a disabler, meaning that it disables the action of popping, so it prevents the balloon from popping. Or we can have alternatives. So for example, the balloon is pricked with a pen. So the balloon will pop, but it was not pricked with a needle as stated in the information that was provided to you. So it is an alternative to that. So let's give a little bit of a introduction on the conditional reasoning domain. So what you saw now, if the balloon is pricked with a needle, then it will pop. That is a conditional. It is a statement of the form if X then Y, where we refer to X as the antecedent and Y as the consequent. In a conditional reasoning task, you're normally given a conditional, so we also call that a major premise, and you're also given the current state of one of the two propositions X or Y, which is called a minor premise. And from that, a conclusion of some sort can be inferred. Here we consider these four major inference forms: modus ponens, affirming the consequent, denying the antecedent, and modus tollens. They depend based on which antecedent in what form has been given as which proposition in what form has been given as a minor premise, and what kind of conclusion can be inferred about the other proposition. So in general, when humans reason with conditionals, it is still not known what kind of reasoning processes actually happen. So this is something that has been attempted to be explained by many cognitive theories for many years. However, not everything could be fully captured, especially with different experiments that aim to manipulate different kind of things. Various effects have been recognized that are also not fully explainable yet. In general, our question is, how also do individuals interpret these different conditional reasoning tasks? When attempting to answer such questions, or to at least find out a little bit more information regarding them, normally researchers focus on all of these inference forms separately. However, in some previous work, all of these inferences have been joined into one tuple, which is a so-called inference pattern that we will get into more depth later. And then the rationality of these patterns has been assessed based on preferential models and ordinal conditional functions. We will talk about all of this in depth later on. What is our goal here? So we want to take these inference patterns and to enhance them, so by a notion of endorsement, so that we could actually apply them to tasks like the one that I showed you with the balloon, where you're asked how likely is it that something will happen. And once we are able to do that, then we can perform very interesting analysis, and we will do that on both an aggregate level, but also on the individual level, because it gets quite interesting. But first, let's see what kind of data we're working with. So we worked with experiments that were presented by Zingman et al. In 2016. In total, we have 199 participants in there. All of them received the same 4 contents. And these contents have a various amounts of disablers and alternatives that can be associated with them. We quantify them with few and many. So for example, the balloon example that you have been introduced to is a content that would have few disablers. So there's not that many things that would prevent the balloon from popping, but it has many alternatives. So there's a lot of ways in which we could make a balloon pop. And yes, to these tasks, the participants provide endorsements as a probability in the interval 0 to 100. And additionally, the contents have been presented twice to them, one as full inferences and one as reduced inferences. A reduced inference basically means that the conditional was not presented, so no major premise. They only got the minor premise, so the state of one of the propositions, and they were asked regarding the conclusion. What was expected and has been shown is that in this reduced inference case, the individuals integrate their background knowledge a lot more, since they do not have this conditional rule that kind of limits their reasoning to some extent. So that will be quite interesting to look into the analysis as well. But first, preliminaries. So balloon example, once again, we have the conditional. If a balloon is pricked with a needle, then it will pop. So we will denote the state that if a balloon has been pricked with a needle with N, if it has not, then with not N. And similarly, if the balloon has popped with P, and if it has not popped with not P. And with that, we then reach these 4 possible worlds in this conditionalist realm, where it was pricked with a needle and it popped, it was pricked, but it did not pop, not pricked, popped, and in the end, it was not pricked with a needle, and also it did not pop. So we have that. We will write the conditional as P given N. So basically that the balloon pops given that it has been pricked with a needle. We want to define an epistemic state psi that models this kind of conditional. And we want to represent this epistemic state as a total preorder. So total preorders on possible worlds like the ones that we have now express some sort of plausibility. So imagine we have these 2 worlds, omega 1 and omega 2. This scenario here means that omega 1 is at least as plausible as omega 2. So they're either equally plausible or omega 1 is more plausible. In general, so non-monotonic inferences can be realized easily as a form of a preferential entailment. So for example, in this case here, we have that N preferentially entails P, if and only if the world NP is more plausible than the world N not P. What that means is that P can be plausibly inferred, given that N is true, and it's more plausible than not P. In that case. And if we have such a preferential entailment, then we have an epistemic state that models the conditional that we want. And this epistemic state is then represented with this preorder here. So we have the world where both NP are true or false, and they're equally plausible, and they're more plausible than the worlds when one of the events has happened and the other one has not. Now we go a little bit into ordinal conditional functions, which are used as implementations of such epistemic states like the one that we mentioned now. These functions, also popular as ranking functions, they basically take a certain world, omega, and then they assign an implausibility rank. So basically we assign implausibility to some sort of plausibilities here. In general, a higher implausibility rank means that the world is less plausible. So a higher kappa, less plausible omega. And we always have to have this one world that is maximally plausible, and it will always be assigned the rank of 0. So let's go back to our balloon now. We have the worlds, we have this total pre-order here, and now we want to have a ranking function kappa that induces this epistemic state that is represented by the pre-order. So yes, we have to have the maximally plausible worlds, which in this case are NP and not N non-P, and they are assigned the rank 0. And then the other two automatically are assigned the rank 1. So we have this ranking function kappa, which we want to have it that it accepts the conditional. It accepts the conditional if and only if we once again have this entailment so that P can be kappa inferred from N, or N kappa entails P. And as we have defined preferential inference before, we have similarly here that this entailment is true if and only if this the rank of NP is smaller than the rank of N not P. So once again, this is more plausible. The world NP is more plausible than the world N not P, which is true in our case with our ranking function. So this is a function that accepts the conditional. If a balloon is pricked with a needle, then it will pop. Okay, so now let's go into inferences. So as I mentioned, we are focusing on these 4 inference forms, and then imagine that an individual uses the modus ponens inference form, but not the modus tollens one, and that has certain ranks on the world that explains that behavior. But then there's another individual that uses MP, not MT, maybe DA, AC. Anyway, there's a lot of different combinations that can influence these ranks. So instead of looking at each inference form separately, we want to look into all of the worlds at once. So we look at all of the inference forms, we look into all of the worlds to see how that influences the ranks. And here's how we come to these so-called inference patterns. So what is an inference pattern? It is basically a tuple, a 4-tuple of inference rules, such that for each one of them, it indicates whether the rule is used or it is not used. And there are 16 possible inference patterns in that case. So let's make this more clear with an example. So we have this 4-tuple here, and basically it simply states that the modus ponens inference form has not been used, whereas the other 3 have been used. Very simple. Before we continue, let's first talk a little bit about plausible inferences. So in order to draw plausible inferences with respect to some inference rule, we have to define a plausibility pre-order on the set of the worlds. So for example, if we have the inference for modus ponens, then it is drawn if and only if for a given conditional, if A then B, this inference is drawn. So A entails B. This is something that we have for obviously all of the inference forms, and basically the corresponding minor premises and conclusions that I presented earlier have to be entailed and drawn. So let's remind ourselves. So if we have a conditional, if A then B, so A entails B. We said already that this happens if and only if the world AB is more plausible than the world A not B. So basically a world omega that verifies the statement, if A then B, is more plausible than a world that violates the statement, if A then not B. So with this, we actually set some sort of constraints that we call plausibility constraints. And again, we have them for each one of the inference forms. So we have this inference pattern here. And in order for this inference pattern to be satisfied, we have to have a plausibility relation that satisfies each one of the constraints for each inference form. So for example, we have this pattern here. MP has been used, and that means we have the constraint that the world AB has to be more plausible than the world A not B. So that is our first constraint. Then for MT, we have this constraint here. Not A, not B, it has to be more plausible than A not B, and so on and so forth. And in the end, we reach this plausibility relation here, which actually satisfies each one of the constraints. So we have this ordering on the worlds. As a note, we now define, so this ordering here, we refer to this as a preferential mental model, and it is, as by definition, a set of possible worlds together with a total pre-order, as we can see in the example. So with this kind of approach, we can, as mentioned earlier, analyze combinations of certain inference rules, whether they were used or not. So here we want to apply this to the data that we previously presented. But as mentioned, there we are dealing with probabilistic endorsements. So people did not just say, yes, this is correct, or no, it is not. So we cannot say that an inference form has been used or not, but they endorsed it. They would say 78%, for example. So we want to be able to represent this using our inference patterns. How do we do that? So yes, a probabilistic endorsement of a conclusion. It's basically the degree of subjective belief that an individual has in the world that is described by the minor premise in the conclusion, and it is given in the range between 0 and 100. The first step towards this is that we take endorsements that are greater or equal than 50% as true. So we interpret in that case that the inference form has been applied. Otherwise, if it's less than 50, then we interpret that as false. So the inference form has not been applied. We then looked into the data that we have. We examined the relationships between the endorsements on both aggregate and the individual level. And we also set a difference tolerance of 5%. What that means is that if there were endorsements that differed by 5 or less, then they're considered as equally endorsed. So this will be clear in a second in this example. So let's see that there's an individual that provided the following endorsements. So 32 for modus ponens, 44% for modus tollens, AC with 88, and DA with 85. So let's look at the rankings between these endorsements. So we first have MP and MT that are less than 50%. So therefore we interpret them as not applied, not used, and they're false. And then we have AC and DA that are true since they're greater or equal than 50%. And then we look first into the rankings in the not applied inference forms. So MP is lower endorsed than MT. So we end up with this ranking. And then here is the difference tolerance of 5 that AC and DA are 88 and 85 respectively. The inference pattern that would correspond to this is the following here. So we have that MP and MT are not applied and AC and DA are applied. However, here still we're lacking the influence of the ranking of the endorsements themselves. So we extended these inference patterns. So basically we have the same definition. We have a tuple with all 4 inference rules in it that indicates whether the rule has been used or not. And additionally, we have statements about the ranking of the endorsements of these inference rules. So for example, in this inference pattern here, we then additionally provide the ranking. So we have MP and MT are not applied, AC and DA are, and then the additional information, the statements about MP being having a lower endorsement than MT, and that AC and DA are endorsed equally. So, okay, now we can move on to explaining human inferences. So first, let's talk a little bit more about disablers and alternatives. So in general, disablers reduce the degree of belief in the logically valid modus ponens. So if we have few disablers, that actually means that the antecedent of the conditional is very informative for the consequence. So these 2 inference forms, MP and MT, should be strong. From that, we have the following expected rankings of the inference forms, which result in this ordering of the world, so that the not A, B world would be more plausible than A, not B. And then consequently, if we have many disablers, then the antecedent is not informative for the consequent, and we have the opposite ordering of the worlds. Then we have a similar approach for the alternatives. So they reduce the endorsement of the logically invalid inference forms. And if we have few alternatives that are associated with the content, then the antecedent seems very plausible when we observe the consequent. So in that case, AC should be very strong. Similarly, we get this kind of ordering on the worlds of the conditional in the case of few alternatives, and consequently, the opposite is true if we have many alternatives. So as mentioned, we first performed analysis on the aggregate level. What that means is that we took the average of the endorsements of the participants for each one of the 4 contents in each one of the presentation forms. So we have the reduced inference form and the full inference. So this is without the conditional, this is with the conditional. Here we have whether the content has few or many disablers or alternatives associated with it. And then this is the ranking of the average values of the endorsements. From that, we found the induced preferential mental models that correspond to this ranking of the endorsements. And these preferential mental models tell us which kind of scenario they actually model. So what kind of scenario is represented by this? By scenario, we mean whether this would be a task that has few or many disablers or alternatives associated with it. What we can see on the aggregate level are results that are not that great in all of the cases. So for example, in this task here, we did not find a preferential mental model, which points to most likely very divergent views between the individuals. And additionally, you can also see how 3 of these are marked in bold. And those are the only scenarios, so the corresponding scenarios to the preferential mental models that correspond to the originally intended amount of disablers and alternatives. So there's the question, did the individuals not interpret these contents as they should have? Did the experiment not work very well? But let's see first how many individuals actually have the same ranking, how many individuals' endorsements coincide with what we have on the aggregate level. Not that many. So we have, for example, in this case, there's only 3 individuals whose endorsements follow the ranking that was found on the aggregate level out of 199. We even have 2 cases when there are no individuals that have the same ranking as found on the aggregate level. So this was a very big motivation to derive rankings on the individual level, so for each individual separately, and then look into the induced preferential mental models for each individual and to see if maybe we have results that give us a little bit more insight into what is happening. That worked out quite well, a lot better than the aggregate level for sure. So because this is quite a big table, I'm only showing you the results from one of the tasks. This is the popular balloon task that has few disablers and many alternatives. So what you can see here is, so these are rankings, different rankings that were found for at least 5% of the participants. So at least 5% of the participants have this following ranking of the endorsements. You can see, so there's 16 out of 199, 15 out of 199. So they're not divided into few largely populated groups, but rather they're quite dispersed into smaller groups. However, they have different rankings, yes, but they induce preferential mental models that actually correspond to scenarios that identify the same quantities. Which coincidentally are also the quantities that the task originally has associated with it. Though there are, for example, in this case, 12 people, that apparently alternatives do not have influence on the reasoning so much, but still it's quite encouraging that we can see the influence in these other 3 groups here. And in this full inference form, we have a much larger number, 46 individuals that actually, whose scenario does not coincide with the originally intended scenario, but this is the expected result. So this is what I mentioned in the beginning. that when individuals are presented with a conditional rule, so in the full inference form, their background knowledge can be suppressed. So maybe they do know about many alternatives related to the balloon. However, because they are given this rule, they suppress that. Whereas in the reduced inference form, they do not, except for these 12 people here. So yeah, the most interesting thing here is that we do have these different combinations of inference forms, and they all actually have the same interpretation. So, okay, let's discuss a little bit. So first, our contribution here has been that we took these inference patterns and then we extended them towards probabilistic endorsements. And with that, we applied them to probabilistic data, actually. And with these kinds of approaches, we can actually see how people understood the given experimental tasks. For example, this task with the balloon was given so that we see the influence of many alternatives, but did people really understand that way? So we can look more into whether the experimental content managed to achieve its goal. So then we were working with disabler's and alternatives that are events that make humans diverge from logical reasoning, and it has been shown repeatedly. We also saw the effect of individual differences on how humans actually reason. So we found these different rankings. However, they're all interpreted the same way, but expressed differently. And a very interesting thing was that, though not surprising, that on aggregate level, we did find inconsistent patterns. And we showed that doing analysis on an aggregate level might not always be the smartest thing to do. And if we want to learn more about human reasoning, we should definitely look more into individuals themselves. So yeah, to conclude everything, we managed to account with our approach for the effect of human diversity in reasoning. We definitely confirmed that the focus has to be switched on to the individual. And I want to mention one particular interesting next step that we could take here is to look into how one individual's subjective beliefs change when they are presented with different contents. So now we looked into the individual ECS, but for example, this one individual has certain inference mechanisms with this content, and how does that change to another content with more alternatives, for example? Or how did this one individual react to the change in the presentation from reduced inference to full inference? So yeah, there's quite a lot of interesting things that we could do in that regard in our future work. Other than that, I would like to thank you for your attention. And if you have any questions or comments, please.